Hello, my name is João Parente, and I'm going to introduce my work titled Effect of Graphene Nanoparticles on Suspension Viscosity and Mechanical Properties of Epoxy-based Nanocomposites. But first, an introduction. Nowadays, nanoparticles are applied in many engineering applications due to their unique surface effects, increased chemical activity, and physical properties. Among these nanoparticles, graphene is one of the most promising due to its excellent mechanical and electrical properties. This makes graphene a good candidate for use in composite materials. These materials are composed of a polymeric resin, usually an epoxy-based resin, and reinforcing materials such as carbon, glass, aramid, or natural fibers. The addition of graphene to these composite materials can improve the mechanical and optical properties as well as the electrical and thermal conductivity of the composite material to which is added. But what is graphene and what types of graphene exist? Graphene is a material composed of carbon atoms with sp2 hybridization connected to each other in hexagonal lattice configuration. Graphene, in all its forms, exists as a powder and is created from the exfoliation of graphite. It can be functionalized with different compounds and is usually mixed in the matrix of the desired material or deposits on its surface. The second type is called graphene oxide. It consists of graphene nanosheets with added oxide-based groups. These groups improve the interaction with the matrix by forming stronger connections, and they also offer anchorage points for the creation of functionalized graphene. The third type is called graphene nanoplatelets. They are composed by several layers of graphene sheets connected by van der Waals forces, one on top of the other. They possess a large overall size, offering a high contact area. This allows the creation of materials with better mechanical performance, especially in fatigue performance and impact performance. So, the objective of this work was to study the properties of epoxy resin and how they are affected by the presence of graphene. So, in our work, we used graphene nanoplatelets supplied by a Portuguese company called Grafenest. We also used a two-component epoxy resin system composed of epoxy resin and a hardener from C-Mast. So, for the viscosity tests, the tests were performed using a rheometer with a cone plate of 2.5 cm of diameter. The tests were performed only in the resin without the hardener so that the polymerization will not affect the measurement of the results. The amounts of graphene used in these tests went from 0% to 1%, and the temperature was kept at a constant 25 degrees. We also measured the contact angle of the resin. For that, we compressed a graphene powder to form graphene wafers with 1 cm of diameter. After that, using a contact angle meter equipment, we dropped 5 microliters of epoxy and hardener to the surface of the graphene and measured the variation of the angle for about 8 seconds. We also studied the shrinkage of the nanocomposite. For that, we used cylindrical molds with 40 mm of height and 25 mm of diameter. We cast the nanocomposite into the mold until it reached the top. After the curing process, we compared the height of the initial nanocomposite with the final height of the cured composite at the lowest point. We also studied the effect of mixture condition on the polymerization. For that, we mixed our resin with graphene and put this mixture into an isolated vessel filled with rock wool so that outside temperature will not affect the measurements. To study this effect of the polymerization, we measured the variation of temperature over time during the polymerization process using a temperature sensor probe. We also studied the effects of hardening mixing time, pre-cure temperature, and graphene quantity on the mechanical effects of the nanocomposite. For that, we varied the hardening mixing times between 0.5 to 5 minutes, the pre-cure temperature between 7 degrees and 40 degrees, and the quantity of graphene, which varied from 0% up to 1%. So to create the nanocomposites, we must follow the following steps. First, we must mix the graphene with the resin for 3 hours at 1000 rpm with ultrasound assistance. This is followed by the addition of hardened with mechanical stirring at 300 rpm for the determined amount of time that you plan to study. This mixture is then put in the vacuum chamber for 5 minutes to remove the air bubbles. After that, we fill the molds with our mixture, which you then pre-cure at 24 hours to the determined temperature that you plan to study, and then we do 24 hours of cure at 40 degrees. After the fabrication process, the samples were tested both in flexural and tensile mode, according to the norms ASTM 790 and STM 638, using a C-Mast AGX universal tester. Now let's look at the experimental results. Observing the viscosity and contact angle results, we can see that the addition of graphene increases the viscosity of the resin, with 0.5% showing an increase of 4.2%. Looking at the contact angle results, we can see that initially the angle of the drop is above 60 degrees, but over time this decreases, showing that the resin has a good ability to wet the graphene. Looking at the shrinkage and the effects of mixture condition on polymerization results, we can see that the addition of graphene increases the shrinkage effect from 3.2% up to 5.9%. And looking at the effects of mixture condition on polymerization, we can see that adding graphene to the mixture lowers the maximum temperature that occurs during polymerization, but this process occurs more rapidly. So, in the study of the hardened mixing time, we can see that 2.5 minutes offer the best results in bending stress, bending stiffness, and bending strain. Further increasing the time does not offer any significant improvements. In the study of the variation of mechanical performance with per temperature, we were able to see that the best results in both bending stress, bending stiffness, and bending strain occur when the per temperature is about 70 degrees. We believe that this is due to a slower polymerization that leads to a better polymeric network. Looking at the results for the variation of mechanical performance with graphene quantity and per-cure temperature, we can see that the best results occur when 0.5% of graphene are added. This, for bending stress, represents an increase between 8 and 31%. We can also see that for bending stress, the best results occur when a per-cure temperature of 7 degrees is used, but for bending strain and bending stiffness, this occurs when a per-cure temperature of 25 to 30 degrees is used. Looking at the tensile test results, we can see that the maximum stress occurs with 0.5% of graphene, a behavior similar to the flexural test results. For higher quantities, we can see a decrease in the maximum stress results. This may be due to the agglomeration effect that occurs in the graphene. Looking at the deformation, we can see that with the increase of graphene, there is a decrease in the values of the deformation. And looking at the stiffness, we can see that with the increase of graphene, there is an increase of the stiffness. Looking at the previous results, we believe that the better results for lower temperatures are due to a slower and more stable cure that form a stronger polymeric network and thus improve the mechanical performance of the material. We also believe that the possible explanation for the better results with the addition of graphene is due to their natural rigidity that improve the bending stress and rigidity of the nanocomposite, while lowering the deformation of the same material. So, to conclude, we can see that adding graphene to epoxy resin can increase its shrinkage and its viscosity. We also concluded that using higher hardened mixing times and lower per-cure temperatures can have a positive effect on the mechanical properties of the nanocomposite. Concerning the graphene content, we could see that the best mechanical properties were achieved when 0.5% of graphene was used, and represented an increase between 8 to 41% of the maximum bending stress. That is all. Thank you.